everyone. In this video, I'm going to talk about heat of reaction. Enthalpy of a system is the sum of the internal energy and the product of the pressure and volume. Enthalpy change is the heat involved in a reaction at constant pressure. Delta H is positive when heat is being absorbed by the system. This process is called an endothermic reaction. When delta H is negative, heat is being released by the system. This process is called an exothermic reaction. Entropy change in a chemical reaction is an extensive property because the more the reactants used, the larger the enthalpy change. Standard condition is a state of material at a defined set of conditions. For pure gas, it is exactly at 1 atmosphere. For pure solid or liquid in its most stable form is at 1 atmosphere and 25 degrees C. Substance in solution with concentration is 1 molar. The standard enthalpy change is the enthalpy change when all reactants and products are in their standard states. Calculating the standard enthalpy change for a reaction involves the summation of the enthalpy of formation of all products minus the summation of all enthalpy of formation of reactants. We have to remember constantly that is the summation of the product minus the reactant, not the reverse. An example: finding the standard heat of enthalpy of formation for this reaction above, delta H of reaction, given the information about the reactants and products. So we have write out the relationship as given. I call this equation 1. Right. So we want to look at the product. For this reaction, our products are NO, 4 molecules of NO and 6 molecules of H2O. We go into our equation. We have 4 molecules of NO and 6 molecules of H2O. For our reactants, we have ammonia and oxygen. 4 molecules of ammonia and 5 of oxygen. We go into the table given and we plot these values in. For NO, we have 91.43. This is 4 times positive 91.3. And for water molecule, we have negative 24.18. For ammonia, we have negative 45.9. When we plug all these things into our calculator, we have the value to be 1085.6, right, into negative 183.6. So this gives us 1085.6 negative plus 183.6, and we have negative 920.0 kilojoule. This means that our reaction is exothermic. For Hess's law, a reaction can be expressed as a series of steps. For the overall reaction is going to be the sum of all the heat of reaction for each step. So we have ways in which we use this Hess's law. and we say if a chemical equation is multiplied by a factor, then the heat of reaction is going to be multiplied by the same factor. If a chemical equation is reversed, the heat of reaction changes sign. If a chemical equation can be expressed as the sum of a series of steps, then the delta H for the overall equation is the sum of heat of reaction for each steps. For example, if you want to find the heat of reaction for this equation, given the series of equations that we have below, we have 1, 2, 3 with their value of delta H. So what we do is we manipulate in such a way to get the reactants of interest on the left and product of interest on the other side. Then we cancel other species out. For this reaction, our species that we need to cancel are going to be oxygen, CO2, and H2O. Because we do not have this in the overall equation, this is the overall reaction, equation of reaction. Alright, so our product of interest is CH3. If you look at the first equation given here, our CH3 is in the reactant side. So we need to make sure that our product of interest is on the product side. In this case, we need to flip this equation, and when we flip this equation, we have to change the sign of delta H. So our first equation gives us this, because we need to flip this to be on this side. So we have this new equation. We flip this and we reverse the sign. Looking at the second equation, we have our carbon, which is a reactant of interest. It's already on the reactant side. However, we have 3 moles of carbon, and here we have 1 mole. So we need to multiply the whole of this equation by 3 so that we can have 3 moles of carbon. And whenever we do so, we have to do that to this. So our second equation becomes 3 of carbon, 3 of oxygen, and 3 of CO2. Then we multiply our delta H with 3. So this becomes the new equation. And we go to the third equation. We have hydrogen, which is a reactant of interest. If you look at this third equation, we also have hydrogen on the reactant. We do not need to flip this equation. However, we have 4 moles here and we have 2 here. What we need to do is to multiply this by 2 so that we can get this. And whenever we do that, as usual, by multiply by a factor of 2, we have to multiply our delta H also by 2. So this gives us a new equation here. We have 4, 2, and 4. We multiply by 2. We can rewrite these 3 equations so that we can remove all the other reactants that we do not want. So CO2 needs to be got rid of. So we have 3 moles of CO2 in the reactant, and also here in the product 3 moles. So we can cancel them because 3 minus 3 gives us 0. Then we come here, we have 4 molecules of water in the reactant, and we have 4 molecules of reactants in the product. So we can cancel this out because 4 minus 4 moles give us 0. Here we have oxygen in the product to be 5 moles. In this reactant, we have 3 plus 2 of oxygen giving us 5. So these two gives us 5 moles of oxygen, and we can cross them out. So we are left with 3 moles of carbon and 4 of oxygen in our reactant. We bring down, and on this product, the only stuff that we have is C3H8. So this equation is now a representative of the overall equation that we are given here, right? So this gives us the permission to add all this heat of reaction for each of these steps together. So our overall heat of reaction is going to be positive 2043 plus negative 1181 plus negative 967.2. When we plug this into calculator, it gives us our heat of reaction. So for this, because our delta H of heat of reaction is negative, our reaction is exothermic. I hope this helps. Thanks for watching.